Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Conditional Probabilities. As always, please be an attentive learner while watching this video. Previously, we learned when two events are independent, the occurrence of one event has no effect on the probability of the second event. However, we cannot always assume that two events will be independent. Will the probability of being in a car accident change depending on driving conditions? Of course. We'd expect that the probability of an accident will be higher for driving on icy roads than for driving on dry roads. Another example, according to data from the CDC, 33.3% of adult men are obese. So the probability is 0.333 that a randomly selected U.S. male is obese. However, 28% of adult men who are from 20 to 39 are obese compared to 40% of men who are between 40 and 59. So the probability is 0.28 that an adult male is obese given that he is 20 to 39. The probability is 0.40 that an adult male is obese given that he is aged 40 through 59. So the probability that an adult male is obese changes depending on his age group. Therefore, obesity and age are not independent. This is an example of what is called a conditional probability. Here's the definition for conditional probability. The notation P of F given E, and we read that P of F given E, that vertical bar is given. Event E is the probability that event F occurs given that the event E has occurred. So for example, in our example, the probability of being obese given your age is from 20 to 39 was 0.28, and the probability of being obese given your age is 40 through 59 is 40%. So here's an example problem. Suppose a single die is rolled. What is the probability that the die comes up 3? Well, that is 1 out of 6 because there are 6 possibilities. They're all equal likely, so the probability of 3 is 1 over 6. Now suppose the die is rolled a second time, but we're told the outcome is odd. What's the probability that the die comes up 3? Well, this time the sample space is 1, 3, 5, and so 3 comes up 1/3 of the time rather than 1/6 of the time. So the probability of rolling a 3, given that the outcome is odd, is 1/3. You see, the conditional probability reduces the size of the sample space under consideration from 6 outcomes to 3 outcomes. Here's a table showing status about being married, divorced, separated, and so on and so forth. We have males, females, and totals, and these are in millions. So we have the rows and columns totaled. So to find the probability that a randomly selected individual 15 years or older, that's what the table is about, is widowed, what we're going to do is we will go to the widowed row, and we'll see that there are 15.2 million divided by the total is 260.1 million, or it is a little better than 5%, 0.058. Now suppose we know the individual is female. Does this change the probability that you're widowed? Well, when we look up here, the number of widowed females divided by the total number of females is, in this case, 11.9 divided by 133.2. You see it was widowed females, so here is the 11.9, and it's divided by 133.2. And we get it is almost 9%. So you see the likelihood is different, and if you are female, it increases the likelihood that you're widowed. And that leads us to the following rule. This is the calculation rule for conditional probabilities. If E and F are any events, then the probability of F given E is equal to the probability of E and F divided by the probability of E. And if you've got numbers in a table, it's the numbers that are in E and F divided by the number in E. In words, it says the probability of an event F occurring given the occurrence of event E is found by dividing the probability of E and F divided by the probability of F, or by dividing the number of outcomes in E and F divided by the number in E. Here's another example. We're using the same table. We want to compute the probability that a randomly selected individual is never married, given that they're male. Given that they're male, that means we're in here, this 126.9, and never married is 46. So this answer is going to be the probability of never married, given male, is the number in male and never married, which was the 46, divided by the number in male, which is the 126.9. We do the calculation and we get 0.362. Part B, we want to compute the probability that a randomly selected individual is male, given that they have never married. Now we're saying we're looking at all the people who were never married. That was 86.1, and the number of them that are male are going to be then 46. Let's consider another problem. So here's a table talking about marital status and gender. So you could be never married, married, widowed, divorced, separated, and so on and so forth. You could be male, female, and we have totals of the rows and totals of the column. So use this table to compute the probability that a randomly selected individual has never married, given that they're male. Well, given that they're male, we look in this column, so it is a total of 126.9, and they were never married as 46. So we look at 46 over 126.9, and we get 0.362. The second question is compute the probability that a randomly selected individual is male, given the individual has never married. So we're looking at never married. That is across here. That is 86.1. People have never married. But if we're looking at if they're male, we're saying it is 46. So this time it is 46 over 86.1, and it's 53%. Now the difference tells you that it makes a difference whether you say the probability of never married given male and the probability of male given never married are not necessarily the same number. Here's another problem. Suppose that 12.7% of all births are preterm. That means that they're less than 37 weeks. Also, 0.22%, that's a very low percentage of all births, result in a preterm baby who weighed 8 pounds, 13 ounces or more. That's a very heavy baby weight, and this is a very small number of babies that are that big being born early. What's the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? Is this unusual? Well, it's unusual if it's less than 5%. So what we're going to do is we're going to compute the probability that a baby weighs 8 pounds, 13 ounces or more, given that they're preterm. So we say, what's the probability that they weigh 8 pounds, 13 ounces or more and are preterm? That is 0.0022. We changed that percentage into a decimal, and that's divided by the probability of being preterm. That's the definition of the conditional probability. So it is going to be 0.127. We do the calculation, we get this, and yes, this is unusual because it's less than 5%. That leads us to the general multiplication rule. The probability of two events, E and F, both occur is the probability of E and F is equal to the probability of E times the probability of F given E. Now you might notice that this is exactly the equation we had for the conditional probability, except we're multiplying both sides by the probability of E. In other words, the probability of E and F is the probability of event E occurring times the probability of event F occurring, given the occurrence of event E. So here's an example of using that rule. So the probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket given that he or she was pulled over, is 0.9. What's the probability the randomly selected driver who is speeding gets pulled over and gets the ticket? So you see, this is the probability of E and F. So the probability of E and F here is equal to the probability of E times the probability of F given E. So that is 0.8, and this is 0.9, so it is 0.72. This is often used in acceptance sampling to decide whether you're going to accept a shipment. For example, the one we saw in a video was about potatoes. So suppose that of 100 circuits sent to a manufacturing plant, 5 of them are defective. The plant manager receiving the circuits randomly selects 2 out of the 100 and tests them. If both circuits work, she accepts the shipment. If otherwise, that it means one or the other or both do not work, the shipment is rejected. What's the probability that the plant manager discovers at least one defective circuit and rejects the shipment? Okay, well, here's 2 approaches. One way is you can make a table listing all the outcomes and do a multiplication. We're going to do this one second. But the other one is to compute the probabilities that both are not defective. And so the solution here is of 100 circuits, 5 are defective, so 95 are not defective. And so that's the solution to approach 2. Now approach 1, we're using the tree diagram, and what we're going to do is go to the next page. And we're going to draw the probability the first is not defective is 95 out of 100. And this is the other branch. So 95 over 100, you are good. And 5 out of 100, you defective. And then you go to the second circuit. And so here, if the first one was good, there's 94 still good out of 99. So this is 95 over 100. And we're going to multiply times 94 over 99 because those are independent, and I will get this number. Now here, what can happen is I can get a good one, but then I can get a defective one. Again, I multiply the probabilities and I get this, and so on. Now, the probability that at least one is defective is going to be the sum of the ones where you have at least one defective. And so it's going to be this number that is getting a good, then followed by a defective. This, the probability of getting a defective followed by a good, and this one, which is going to be the probability of 2 defectives. And we get those from the tree. Okay, so here we're drawing a tree diagram. So for the first circuit, you have 95 good ones. So the probability of getting a good one on the first selection is 95 out of 100, and it is 5 out of 100 getting a defective. So this is good, and this is defective. But then the second circuit, now you have picked one, you don't put it back, and so you have 99 to choose, and 94 of them are good because you took a good one already. So you took one and it was a good one. So this is 94 over 99, but you still now have 5 bad ones, and it's 5 bad ones out of 99. So the chance of getting here a defective is 5 over 99. Now, what happens is if you got a defective on the first one, you still can pick a good one here, and so that is 95 out of 99 because they're all good, and you have picked a bad one. Or down here, getting another defective is the probability of giving a second defective, given the first was defective, is 4 out of 99. Now, the question that was being asked is, so the probability of at least one defective, which means you will reject the shipment, is the probability of getting a good followed by a bad, or getting a bad followed by a good, or getting 2 bad. So that is going to be this number, and this number. We got those all from the table by multiplying the independent probabilities. So the probability that will not be accepted is this, almost 10% of the time. Or, what you could say is the probability of at least one defective is 1 minus the probability of none being defective. So 1 minus, this is the first not defective, was that, times the second not defective would be that. And so multiplying these, I get this, and I subtract, I'll get the same number. So we have two approaches. Whenever a random sample is taken from a large population, it's reasonable to assume that the probabilities of the event are independent, even though they're technically not. Okay, so suppose we have a study where we are to determine the preferences for South are more or less prevalent than preferences for others. So researchers first ask individuals to identify the person who is most valuable and likely to you, or your favorite other. Of the 1,519 individuals surveyed, 42 had chosen themselves as their favorite other. So suppose we select one of the 1,519 people. What's the probability they chose themselves as a favorite other? It's going to be 42 divided by 1,519. Now, and you see it's 42 over 1,519. You do the calculation, you get this number. Now, the second question is, if two individuals from this group are randomly selected, what's the probability they both choose themselves as their favorite other? Well, you see here you would have 42 over 1,519 times 41 over 1,519. You would get this number. Now, notice that the probability of event 2 given event 1 is this. Because we're sampling without replacement, you don't put the other person in. So event 1 occurs, there's one less person who considers themselves the favorite other, and one less person in the sample space. But if we do it just assuming they're independent, 42 over 1,519 times 42 over 50, you see the number doesn't matter too much, and that's the point of that assumption that we could make, and you see that it really doesn't make a difference if the n is a very big number, and we're talking about less than 5% of the number. Okay, so this is the rule of thumb. If the sample size is less than 5% of the population size, you can treat them as independent. And now we're ready to express independence using conditional probabilities. This is an alternative but equivalent definition. We can say that two events, E and F, are independent if the probability of E given F is equal to the probability of E. It doesn't matter whether F happened or not, or the probability of F given E is the probability of F. And notice that since we had this characterization before, the probability of E and F equal the probability of E times the probability of F, these two things are equivalent. And just to give you another example, the probability of widowed, 0.58 does not equal the probability of widowed given female. That means they're not independent. In fact, knowing an individual is female increases the likelihood that the individual is widowed. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other, because we're all in this together. God bless you all.